In the last video, I looked at the full model for predicting the number of physicians there would be in one of these small cities. And the full model just means that we used all of the variables available to us, the hospital beds, the income, and the density. And we talked about the fact that density did not make a very good contribution. Let's try another model, this time without density in it, and compare the two and see what kind of change we get. So I'm going to, again, create a code chunk here, and I'm going to do a little bit of laziness. I'm going to go ahead and copy and paste my full model and then revise it a bit. I'm going to call this the beds income model, and I'm going to take out density. And then we want a summary of the beds income model. Okay, let's go ahead and run this. And so here we have, again, our two different estimates for beds and income. Notice if you compare, you'll see a little bit different coefficients. That's because in a multiple regression model, the coefficients all depend on the entire collection of variables. So we didn't have much of a change for hospital beds. Actually, we didn't have much of a change for either of them, but we did have a little bit of change. Okay, this was 15.57 for income. Now it's at 14.99. This one was 0.035. Now it's 0.032. So we did have a little bit of change. Sometimes they can change quite a bit. We do still see, however, that they're both stable. Sometimes what will happen is that when you take out one variable, all of a sudden the p-value changes very drastically for the other variables. That's because we're dealing with these variables that are correlated to one another and they can influence each other. Again, taking out density didn't matter that much because it didn't seem to be correlated very highly with any of the variables that are in our data set. But now, how can I compare these two models? Well, let's look at the concept of the coefficient of determination again. The coefficient of determination, the sum of squares total, is the error of prediction when the explanatory variables are not used. That is, simply taking our observed value and seeing how far the deviation is from the mean, just like we did with simple regression. The sum of squares error is still the sum of squares of those residuals. Even though we have multiple variables, they lead to a single prediction, and you take the prediction minus the observed minus the prediction, and you in fact then would end up with an error, a residual. So rather than me trying to describe it, let me just go ahead and remind you here where you can see it. So with the residual, we have y minus y hat. That is the observed minus the predicted, and that's the residual. And so even though we have multiple values of coefficients, multiple explanatory variables with multiple coefficients, we still have one predicted value that we get from that. And then, of course, for total, we have y minus y bar. So when we're looking at those sums of squares, we're looking at the sums of squares for the residual, sums of squares total, and the difference between those two would give us the sums of squares model. The other difference that you'll note is this is a capital R squared. So capital R is referred to as the multiple regression coefficient. It's like Pearson's coefficient, except that it is when we have multiple explanatory variables. So for Pearson's coefficient, we have R. For the multiple correlation coefficient, we have capital R. And then, of course, whether it's little r squared or big R squared, it's still the coefficient of determination. So looking back over here and at these models, notice something right here. Multiple R squared, that's your coefficient of determination. And it's 0.2855, meaning that 29% of the variation in the physicians, the number of physicians across the cities, can be explained by or is associated with, we don't know that it's causal, but is associated with hospital beds, income, and density. That is the combination of those three. Down here, notice that the multiple R squared is lower, but how much lower? It went from 0.29 up here to 0.27 down here. That is, we reduced the number of explanatory variables by a third, going from 3 to 2, and we only went from accounting for 29% of the variation in physicians to 27% of the variation in physicians. So what we find by looking at that is that a reduction of one variable doesn't cost us very much. And we would like to have as simple a model as we could. So I am not going to use this model up here in which we looked at all three of the variables, but instead I'm going to look at this model down here in which we used only two of the variables. So that's what the multiple R squared and is about up here and down here. Now, one thing I will tell you about a full model, that is when you use all the variables, it will always have the highest R squared. It will always have the highest R squared. The idea is that, well, more than the idea, the actuality is that every time you put another variable in the equation, even if it's almost meaningless, you can increase the R squared by a little bit. The correlation coefficient, not that I need to use that, I always will use the R squared, but if you ever hear someone talking about, well, what was the multiple correlation coefficient, it's just the square root of this value. So I don't see a need for that because that isn't as interpretable as, in fact, when we have the actual R squared, which can be interpreted as the proportion of the total variation that's accounted for by the model. Then there's another value you'll see over here called adjusted R squared, and notice these are almost identical. What adjusted R squared is meant to do is to make an adjustment for the number of variables you have. So the fact that we have two variables down here and three variables down here, sometimes what you can have happening, it didn't happen in this case, but sometimes you can actually have a smaller number of variables, explanatory variables, with a larger adjusted R squared. That will never happen with multiple R squared, but it can happen with adjusted R squared. Whereas the multiple R squared will always increase when you put in another variable. The increase for the adjusted R squared is actually how much the new variable you're putting in increases the model R squared above what you would expect by chance. That is, anytime you add a variable, you're going to expect an increase in R squared just by chance, even if it has nothing to do with the response variable, because there's always going to be a non-zero correlation among those. But it adjusts above and beyond chance. R squared, adjusted R squared is always going to be less than the multiple R squared. Okay, it's always going to be less than the multiple R squared. But we notice here that the amount that it went up from two variables, 0.239 or 0.24, to three variables, 0.24, is basically not at all. And so in essence, we're saying that that variable didn't add anything. Adjusted R-squares can be negative, which is a little bit strange. Multiple R-squares can never be negative, but because of the adjustment, sometimes it will bring the value below 0. Okay, so before we leave here, let's try to do, let's see what the variables would be like if we just had one variable in. And actually, we can answer that question because we have the correlations up earlier here. If I had only had hospital beds in, then I had a correlation of 0.296. So if I take 0.296, that is with physicians. I'm looking right here at this number, hospital beds with physicians. So if I take 0.296 and square it, that's what my R squared would be with just hospital beds. It would go down to 0.09. I don't even need to build a model because that would become a simple linear regression, and the coefficient determination is just the square of Pearson's correlation coefficient. With income, which that one is 0.433, if I square that, I would have 0.18. So notice that we have a substantial drop in R square if we remove either beds or income. So I'm going to take the combined information knowing that having beds and income together are going to give me a much better R squared, that is, account for much more of the variance than in physicians than I would have if I used either one individually. And I'm going to combine that with the knowledge that these are stable statistics. Remember those high t values, those low p values. These are stable statistics. That is, the estimate relative to the standard error is large enough to be able to say that I expect to be able to use that for any inference outside this study. If I were to do this study again, I would expect those to continue to be stable. So all of that information combined allows me to say, this is a good model. It's the one I'm going to settle on. So I'm going to go ahead and take out at this point the full model. I'm going to put in just the, what did I end up taking out? More than I wanted to there. I'm going to put in just this model with the beds income, the beds income model, and have that one. Now, I don't want all that output to show up in my report. So I'm going to go ahead and just, I don't want any of that output to show, so I'm just going to say show nothing but run the code. We've already looked at the output, so we don't need that output there now. And let me also go ahead and say something about my finding here. So I'm saying that a multiple regression model to predict the number of physicians from the number of hospital beds per capita income in a small city has a multiple correlation coefficient of 0.52, a coefficient of determination of 0.27. That is 27% of the variation in the numbers of physicians in small cities can be explained by the number of hospital beds and the per capita income in those cities. Why don't I also go ahead and give the regression model? So let's go ahead and put that. Here is the model for predicting the number of physicians in a small city from the number of hospital beds and per capita income in the city. And let me actually put a separate line down here so this appears on another line. There it is. If you say, where do you get those numbers? It was from running this model that we're now hiding. However, look up in my console. It's still available right here in my console. And so I can get those values in order to put them down here. Okay, now let's spend just a moment talking about what these coefficients mean. Remember, in simple linear regression, it was for every unit change in the explanatory variable, the average change that you would expect to see in the response variable. Same thing here with one caveat. It's if we hold the other variables constant. So let's see if we can interpret this. So hospital beds, I'm trying to remember. Let me go back and look over here again. Hospital beds, number of hospital beds per 100,000 residents, just like physicians. And so for every 100 hospital beds per 100,000 people that we increase, every 100 per 100,000, so that would be every 1 per 1,000. So we could say it that way. And you might say, well, wait a minute, why are you saying every 100? Isn't it per every unit? I'm trying to convert this into a 3. So I'm going to, instead of taking a jump of 1 unit, I'm going to take a jump of 100 units. 100 units would be 100 hospital beds per 100,000 people, or 1 per 1,000 people. So for every additional bed per 1,000 people, we end up with 3 more physicians per 100,000 people. Now that might take a little bit of sitting and replaying this video and thinking about it, and that's okay. I could have said it this way. For every 1 hospital bed per 100,000 people increase, we increase the number of physicians by 0.03, or 3/100ths of a physician for every 100,000 people. That's worse yet, is it not? How are we going to have that many physicians in our increase? So to change this to be 3 physicians per 100,000 people, I need to multiply by 100, and that's 100 per 100,000, 100 hospital beds per 100,000 people, which is the same as saying 1 hospital bed per 1,000 people. And now let's add that little caveat. If we're holding the median income of the city constant. If you're changing to a city that has a different income, then we don't expect to have that same number of change in hospital beds. So when holding the income constant. Similarly, let me go back here and look and remind myself what income is. It's annual per capita income in thousands of dollars. So similarly, coming here, for every 1 increase in income, which would mean $1,000, for every $1,000 per capita, for every $1,000 per capita annual increase, we expect to see 15 more physicians. So you notice that as the income level of the town rises, we have even a greater effect on the physicians than when the number of hospital beds rises, although that's hard to really say because they're 2 different units. One means thousands of dollars, and the other one means per 100,000 people. So it's really hard to compare the apples and oranges there. And again, the caveat, if we hold the number of hospital beds constant. So saying it again, for every $1,000 increase in per capita annual income, while holding the number of hospital beds constant, we expect an increase of 15 physicians per 100,000 people. A lot to say there, but that's pretty much the way it goes with multiple regression, especially when we have codes like we often will have like this, where it's per 100,000 or in thousands. It's not everything is going to be in nice, clean, easy units. So you have to think through that. Okay, so that's where we're at so far. We still have some work to do ahead of us. Let me go ahead and actually save this and knit it and see how it's looking. See if it gives me a nice clean look. There's my table, Here's my multiple regression. I might want to put in a little space here to separate the table from the text. I don't necessarily have to. I don't think that's as difficult to see as it was up here with this figure, because the figure left so much space in here, but the table doesn't. So I think it's good the way it is. All right, I'm happy with where this is so far, but I've got more to do, and so I'll see you in future videos.